So again, the point that I mentioned a minute ago is the way to get good at this stuff is to practice. And so go through these again and practice them, all right? So these are the proofs here that we're going to be looking at. Show that the statement every integer is less than or equal to its cube is false by finding a counterexample. Give a proof by contradiction of if n is an integer, therefore 3n plus 7 is odd. And finally, prove that this statement is true for all integers n, that n is odd if and only if 5n plus 3 is even. Those are the three. Okay, let's take a look at them. Here's our first one. So this one is telling you, give a proof by counterexample. In the real world, you're not told, hey, here's a proof, solve it by counterexample, right? It's just, I've got this idea, this theorem that I need to make sure is true, and I need to prove it, this conjecture, and I want to prove it, so I have my P, therefore Q statement, right? And so P is the known value, that's our hypothesis, Q is the conclusion, right? Well, when you have a proof, the first thing you should do is quickly look and see if there is a counterexample. Like just quick glance, can I quickly see an easy counterexample, right? And if you can't, then move on. But always try that first. I mean, there's no sense in going through all this crazy math if you can just literally point, oh, there's the counterexample right there, right? And this one, I just gave you a heads up that there is going to be a counterexample. And I think, though, if I didn't tell you there's a counterexample, you'd probably figure that out pretty quickly, right, by looking at that. Because I can, if I said prove that's false, and that's all I said, you could look at it and go, well, what about this case? That's obviously not true, all right? So take a look at this statement here. Negative 2 that's our n, let's say, that's some integer, is greater than negative 2 cubed. Why is that the case? Well, negative 2 cubed, whenever you cube a negative number, what do you get as a final result? A negative number, right? And negative 8, which is what that would evaluate to, is actually less than the negative, or less than negative 2. So negative 2 is greater than negative 8. So thus negative 2 is not less than its cube. Follow? That one's just finding a counterexample. And here is an obvious point here. There's our counterexample. But here's something that is more counterexamples here. Every negative integer is a counterexample to that statement. Every one of them. Okay? And also note that I just put here greater than, but this would also hold, this would still proves that it's not less than or equal to, right? Still proves that statement, right? Because it is greater than. All right, so that one's pretty simple, just straightforward. Just find a case where this piece right here is false and you are done, okay? Questions about that one? That's a pretty easy one to walk through. We good? Okay. So next up, give a proof by contradiction of the following. If n is an even integer, then 3n plus 7 is odd. And if you're watching the video, pause right here for just a moment, try to work this out yourself. All right, let's walk through this. Proof by contradiction. Again, in the real world, you're not told, hey, do this by this method. It's going to be a proof by contradiction, right? You're not told that in the real world. You just assume that I'm going to try a direct proof and it's going to work. And then somewhere along the way, it won't work, all right? So in this case, I don't think we're going to show that it didn't work, but we're just going to go on to the contradiction. So to give a proof by contradiction, we always assume that the opposite of our original claim is true. So what's the opposite of our original claim?
If n is an even integer, then 3n plus 7 is even?
Yeah, so my original claim is this. I'm saying in the event that this P occurs, therefore this Q will occur. Well, what's the opposite of that? That when this P occurs, this Q does not occur, right? That's the opposite of that. So the first step in a proof by contradiction is to claim the opposite. So I'm going to claim that if n is an even integer, therefore 3n plus 7 is also even, i.e. not odd, right? Okay, so we assume that if n is even, then 3n plus 7 is not odd. It's even. Okay, dig it? Make sense? Okay, so therefore we know, this is again our known thing, our P on the P therefore Q, is that n is equal to 2k, because k is an even number, or 2k is an even number, right? That's how we explain an even number. So if I know this to be true, right, how do I know this is true? How do I know that's true? Right, but how do I know that n is even integer is true? You're right.
We're assuming it is.
Yeah, that's our hypothesis. That's our entire point of our proof, right? The P and a P therefore Q statement, P is the hypothesis, Q is the conclusion, right? Our hypothesis is if n is an integer, therefore Q whatever, okay? So I should say if n is an even integer, that's our hypothesis. Well, if n is not an even integer, I don't care. I'm not trying to prove anything about when n's odd. I'm just trying to prove when n is even. So in the event that n is even, that's what I'm doing, then I need to prove whatever Q is going to be, right? So n is equal to 2k, and so that we also are trying to prove this. We don't know this to be true yet, but we're trying to prove that. We're claiming that 3n plus 7 is equal to some even number, okay? That's what we're trying to claim. So for some integers k and j, that's the definition of an even number, all right? Okay, everybody with me so far? Makes sense? Okay. So algebraically, let's just start doing some plugging and playing here. If I take my claim, 3 times 2k plus 7, right? I've just plugged in my 2k right here, right? I replaced this n right here with this, yeah? My claim is that's going to equal some even number. Everybody see that? That's my claim. So I substitute those numbers in. Well, what's going to happen here? Let's just try to solve this and see what we can do here. Would everybody agree with my algebra there? 6k plus 7 is 2j. Again, we're making a leap here that Q is true. We don't know it to be true, but we're just going to walk through it and see what happens here, right? Okay. So mathematically, we still okay? Right? I just subtracted 6k from both sides. Yeah? And then I just flipped what's on the left and what's on the right. Everybody see that? Okay. Next up, I factor out a 2, and I get 2 times something, some constant, we'll call it L or M or N, I think I called it X in the next slide, equals 7. So j minus 3k equals some integer x, so 2x equals 7. What's wrong with that statement?
Impossible.
That's not true, right? It's not a true statement. 2x is the form of an even number. We know 7 to be an odd number, so this is a contradiction, okay? Now, a lot of you, what you did, which was also correct, was right here, you'll see that I plugged in, I put the 2j here, because what I'm doing is I'm assuming that my opposite hypothesis is true, that my opposite, the contradiction is true, that the opposite is true, right? I'm assuming that this statement is not true, that this will be even instead of odd. That's what I'm assuming. So with that assumption, I went ahead and plugged in just assuming that that would be true. So if I'm assuming it's true, let's just run through the math and see if it is true. Turns out we get some weird mathematical contradiction that's impossible. For those of you who didn't do that, what you did was this. You just took this and ran with it. And then you evaluated that and you discovered that that ends up equaling an odd number, right? Since it equals an odd number, what have you proven? You've proven that 3n plus 7 is odd, right? Well, remember, we're trying to prove that 3n plus 7 is not odd. That's our opposite proof, right? Does that make sense? Okay? So you just proved that this squared area is not true. Therefore, the original thing is true. Can you follow all that? It's kind of messy, right? In a proof by contradiction, you try to take the opposite and prove it's true. If you prove the opposite's true, then the original claim is false. If you prove the opposite's false, the original claim is true. You dig it? Okay, what questions do we have about that? So you conclude it by saying, in this equation, the left side is even and the right side is odd, which is a contradiction, okay? Therefore, our temporary opposite claim is false. And if our opposite claim is false, therefore our original claim is true. Right? Now the question came up when we were in teams a minute ago. What makes it so that if our opposite claim is false, therefore automatically our original claim is true? And what makes that work is that in a proof, that's all you're trying to do is find the truth value of something. Well, truth values can only be one of two things, true or false. It can't be both. It can't be neither. It's always true or false. So if you've proven the opposite of something true, then the original thing is false, and vice versa. That's how proof by contradiction works. Feel okay about that? Okay, fabulous. Third one. Prove that this statement is true for all integers n, which is if n is odd if and only if 5n plus 3 is even. Again, pause the video, take a minute to try this out yourself. Okay, so the first thing we got to do in this kind of proof, what kind of a statement is this? You guys have all walked through these already, so tell me, what kind of a statement is this?
Biconditional.
So the biconditional statement, right? In a biconditional statement, how do we know that's a biconditional statement? Because of this fabulous phrase right there, if and only if, okay? When that occurs, then we are trying to prove two things. If and only if, the biconditional, that looks like this right here. This is what that looks like. P, if and only if Q. What that means is simply that this is true and this is true. We're trying to prove both of those. So we need to walk through a proof of, we'll call the one on the left A and the one on the right B or whatever, and try to prove that those are both true, okay? So this is what we're trying to prove. If n is odd, therefore 5n plus 3 is even. That's P, therefore Q. And then Q, therefore P is, if 5n plus 3 is even, then n is odd. Make sense? Okay, so let's do part A first. N is odd. That's our given. That's our known. That's our hypothesis. N is odd. And then by the definition of an odd number, we get this. Okay, everybody good there so far? Okay. So algebraically, what do we get? What can we do here? If we know that n is odd, what can we do? Yeah, just plug it in, right? Because this is our known. We're only doing A right here, right? This is our known. That's our hypothesis. That's our P. This is our Q. We're trying to prove that this part here is true. Well, how can I do that? I'll just plug in what I know the value of n is. I'll plug it in right there, okay? So we do that, and we get 5n plus 3 is equal to 5 times 2k plus 1 plus 3. Everybody agree that that's a true statement? All right, let's just do a little bit more algebra stuff here, and we end up with this. That equals 10k plus 8, agreed? Okay, what can I do next? What am I trying to do?
Prove that that is equal to 2k.
Yeah, that's equal to 2 times some integer, not necessarily k, right? Because k is already in play here. But 2 times something. So we're looking for this form that looks like the 2k, the 2l, the 2 whatever, right? So I'm trying to manipulate it to look like that. So if I want to manipulate it to look like an even number, then I need to factor out a 2, right? Because it's going to be 2 times something, right? So we end up with this, 2 times 5k plus 4. We just factored out a 2, and we're just going to claim that 5k plus 4 is equal to some integer x, and we're left with 2x, which is even. Make sense? So we have proven, just by plug and play, that when n is odd, 5n plus 3 is even. We good with that? Okay. So now that we have that, let's there's our final conclusion there. That's 5n plus 3 is even. Let's take a look at the next step and prove B to be true, okay? There's some nice little highlighting there for you, okay? Sometimes I put too much stuff on my slides, and I could do with 2 or 3 less slides. All right, next up, let's prove B to be true. Well, we're going to try 5n plus 3 is even, therefore n is odd. What's our given? What's our known? What's our hypothesis?
5n plus 3 is 2 times something.
Yeah, 5n plus 3 is even, which is 2k or whatever, right? Okay, that's our hypothesis. So what we would try a direct proof, right? That's always the thing you try. Try a direct proof, and it's going to fail. We'll quickly see what that looks like. If I made this assumption here that if 5n plus 3 is even, then n is odd, my direct proof, my next step would look like that, right? I'm just trying to solve for n. And why am I trying to solve for n?
You want to see if it's even or odd.
Yeah, that's the whole point, right? I'm claiming that when this occurs, this will be odd. Well, that's easy enough. Just solve for n right here, right? So algebraically, we're going to try to solve for n, and quickly we discover this mess right here. Is that odd or even? I have no idea. There may be some crazy math to figure out to get that to evaluate to an odd or even number, but that's just too hard. So you see that, and you're like, all right, this is going nowhere. Let's try a different kind of proof. What's the next thing we should try? Contrapositive, right? Look for a quick, easy counterexample. If you can't find that, direct proof. If that doesn't work, go for contrapositive, okay? So what's next? We try a proof by contraposition, okay? And look at that. I put all of them on one slide for you. I forgot to break them out. So you get to see it all at once. Let's just try to walk through it here, okay? Let me just make sure that, yeah, they're all there. Yeah, they are. Look at that. Sorry about that, guys. I meant to break those out into multiple slides. So, but too late. We're recording. So the contraposition, this is our starting point, right? Agreed? Well, what we're then saying now, instead of that, we're saying if the contraposition, which is if n is not odd, right? If this is not odd, therefore 5n plus 3 is not even. And this is not even. That's a contrapositive, okay? So in other words, it just becomes this statement right here. Right? Okay. Now, what is our given? What's our known? What's our hypothesis? Yeah, n is even, therefore n is equal to 2k, right? And then we just plug it in and see if this becomes an odd number, all right? So let's just see what we can figure out here. So if I plug in my 2k right here for the n, right? I'm saying 5n plus 3 equals that. Agree with my math? Yeah? Which evaluates to this next line right here. This next line right here, it evaluates to that. Look at each of these steps here and make sure that you're agreeing with the math, right? So now we get 5 times 2k plus 3 is equal to 10k plus 3. Now look what happens here. 10k plus 3, we set it equal to 10k plus 2 plus 1. Why did I do that?
Factor out of 2.
Yeah, but why did I break out that 1 like that? Why would I even think to do that?
If you keep it up, if they can turn odd.
Yeah, what we're trying to do is prove that this is an odd number. We know that an odd number takes the form of 2k plus 1 or 2 something plus 1, right? So I'm going to just separate my 3 into two numbers, 2 and 1. That's still mathematically correct, but that allows me to be able to sort of manipulate it into looking like a 2k plus 1 type of a thing, right? And so the next step you can see right here, we just put that parentheses around that, which is you're allowed to put parentheses wherever if they're all addition or whatever, okay? Follow that up, we end up turning that into this. So what do we have there? 5k plus 1 is just some x, some constant x. So we have this final conclusion right here, which is an odd number, right? So our contrapositive claim is true. Not sure what the heck happened there. That was weird. Our contrapositive claim is true. If our contrapositive claim is true, then the original is also true because contrapositive and the original are logically equivalent. They both have the same truth values, no matter what, all right? So with that being the case, let's take a look at what's going on here. If A and B are both true, then our original claim is true. And if our original claim is true, then we have proven our statement that for all integers n is odd if and only if 5n plus 3 is even. How do we feel about that? I know it seems kind of tedious, but try them again. Walk through them again. It's good practice to walk through a proof that you already know. Take that hummingbird proof, right? That's it's in the previous set of videos, and there's also a PDF in Canvas that you can download of the hummingbird proof. Walk through that. See if you can come to that conclusion yourself. It's good practice to do that. Okay, any questions?